Good morning. All right, we finish up DC circuits today. We'll talk about internal resistance of a battery, EMF, things like that, terminal voltage, and then work a couple of problems and call chapter 10 and DC circuits done. Monday, no class, holiday, 3-day weekend. No labs next week. We'll take next week off from labs due to the holiday. And on Wednesday, we will start our new unit magnetic fields, but that will not be on the exam on Friday, a week from today. We have our exam on DC circuits that's up through chapter 10. Okay. So we've been using this symbol. What this symbol really means is an ideal battery, right? We've talked about ideal meters. Ideal voltmeter has infinite resistance. An ideal ammeter has zero resistance. An ideal battery has zero resistance. So this is an ideal and what does that mean? No internal resistance. So it always provides the set voltage. Yes. I don't know what's gotten into them. Okay. But in the real world, we know that our batteries and power supplies have some internal resistance. How do we deal with that? Well, we just put a resistor in series with this, right? That's how we deal with it. And we know how to deal with things like that. It's just like any other circuit we have with the power supply and a resistor. And now instead of this being the battery, now this is the battery, right? So we put on our X-ray vision glasses and look inside the battery. And what do we see? We see an ideal battery in series with a little resistor, R internal. These would be the terminals of the battery. And we use this script E that stands for EMF. That's the maximum voltage. That's the voltage we would get across the terminals when no current is flowing. EMF is an antiquated term. it stands for electromotive force, but nobody really uses that anymore. But we still call it EMF, but even though we don't use the term electromotive force anymore. That means that the terminal voltage, if we measure the voltage across the terminals of the battery, it's always less than or equal to the EMF. When we're flowing current like this, when the battery's providing the power in the circuit. There was a problem, a homework problem in the textbook where they were charging a rechargeable battery and asked what the terminal voltage was, and the terminal voltage was greater than the EMF of the battery because you're running the current backwards through that battery. But when the battery is providing the power for the circuit, the terminal voltage is always less than or equal to the EMF of the battery. So why is that? You're coming in, let's just think of it like our hiking trail with elevations. We come in the low side of our, I'm going to redraw my battery over here. We come in the low side. Let's just call that 0 volts. You go up, you come through the battery, you go up by the EMF of the battery, right? Whatever that voltage source is. We've just risen, right? We've had a voltage rise of that amount. If this is a 1.5 volt battery, we've just gone up by 1.5 volts. Now the current goes in this direction. Okay. The current is going in this direction. So as we continue in this direction, we are going with the current through a resistor. So we're dropping by the voltage across the resistor, IR. And then we come out the other side. So this is the terminal voltage. We go in at one terminal, we go through the EMF of the battery. That's our voltage rise. We go through the resistor in the same direction as the current. So we are dropping by IR, and then we're at the other terminal of the battery. Now you can see that these are equal when I is 0. If I is 0, then the terminal voltage equals the EMF of the battery. As soon as you start to flow some current, if that battery has internal resistance, the voltage across the terminals drops a little bit. And the more current you flow, the more it drops. The battery tries to maintain a constant potential difference, but it struggles to do that as the current increases. All right, let's do a quick recap of our lab that we had earlier where we measured the internal resistance of a function generator or battery. Here's our battery or power supply. So it's really like this, but I just draw it like an ideal battery with the resistor in series. I don't care that it's all inside of the battery or the power supply. I just draw it like a resistor and an ideal battery. So what did we do? First thing we did, we took our voltmeter and we hooked it up like that. And then the second thing we did, we hooked up a resistor. A load resistor, some external resistor, right? So what does this tell us on the left? The first thing we did was just hook up our voltmeter, and we'll assume our voltmeter is ideal. That means it has infinite resistance. So we hook it up across the terminals of our battery. No current can flow. What's it measuring? The EMF of the battery. Okay, now we know the EMF of the battery. Then we hooked it up across the resistor. I'll call this 1 and this 2. This is equal to I times our load. We have to know what our load is. So now we know what the current is in the circuit. We know the current. We also know that V2 is the terminal voltage. You see that it's hooked up to the terminals here. The terminal voltage is E minus Ri, R internal. We know the terminal voltage, that's just V2, we just measured that. We know E, that's just V1, we've measured that. We know I, so now we can solve for R internal. Yeah, V1, get out your colored pens there and check what V1 is measuring. This side is hooked up to the low voltage side of your source. The other side is hooked up to here, but there's no current flowing because a voltmeter has infinite resistance. So the voltage drop across the resistor is 0 if there's no current flowing, right? V equals IR for a resistor. So I can just extend this down to here, and it's measuring the EMF. All right. So our lab, unfortunately, the lab was what, about 2 weeks ahead of the lecture here. Now you're probably looking at this going, "Oh, that wasn't so hard." When you got it in lab, it looked a little crazy. You probably didn't really understand what was going on. But go back and take a look at it now, and I think you'll see that it's really not too bad. Okay. All right. Let's do a problem. How about this one? Okay, I'm getting a package. All right. So while you're thinking about this problem, I will grab my package and quiet my dogs down. One of the things you want to look for when you see problems like this is the switch been open for a long time? Has it been closed for a long time? Things like that. What state is the capacitor in? Okay, have we done part A yet? Finding the time constant before and after the switch is closed. Let's just worry about before the switch is closed. Time constant before the switch is closed. Because these are all in series together, we can just treat R1 and R2 as series components in this circuit. And our equivalent resistance is just R1 plus R2. So what's our time constant? Yeah. Okay. Now we close the switch. What happens? This short down the middle basically separates the two halves of the circuit. The battery is trying to flow a current on this side. I'll use green. Where does that go? When it gets over here, where's that current going to go? It's going to go this way. It's not going to affect the capacitor at all. And the capacitor is trying to flow a current. Where's it going to go? It's going to go this way. We could just separate the two of them. It's it has a zero resistance path back to the battery. So it takes that. So tau is R2 times C. Now it's asking for the current through the switch. It wants to know the current in here. What does that mean? That means we have to add up. We have to add up the green current plus the red current. The current due to the battery plus the current due to the capacitor discharging. The current due to the battery, what's that? That's the easy part. Yes. Yeah, we'll get there in a second. So what do we get here? We say the current from a discharging capacitor in an RC circuit is I maximum e to the minus t over RC. And what is I maximum? That's that initial current that flows when the capacitor is at its maximum charge. So it's the voltage on the capacitor. It's like acts like a battery at that point, right? The voltage on that capacitor divided by the resistance R2. And what is the maximum voltage? The battery, because it was charged up by the battery. Oh, which R? R2. That's an R2. It should be in R2 times C. It's a minus sign. We good? The formula is, well, first of all, this is a discharging capacitor. Right? Where is this red current coming from? It's coming from the fact that the capacitor is discharging. That's a discharging capacitor that's forming the current. But the formula is the same for current, right? Here we have charging. Charging capacitor. Charging capacitor. Q as a function of time. Right? Let's see. When t equals 0, we get 0, right? When t equals infinity, we get Q max, right? That's correct. And the current as a function of time what is Q maximum? Q equals CV, right? So the maximum is just the whole battery across the when the voltage is equal to the whole battery voltage. And I maximum occurs right at the very beginning. When the very first current starts to move, the capacitor, it's almost like the capacitor is not even in the circuit at all. So it's just a battery and a resistor. And then as soon as charges start to build up, a split second later, after you close the switch, the current starts to drop down from that. But for a discharging capacitor, the Q charge on the capacitor as a function of time, that has a different formula, right? One of them starts at 0 and it goes to maximum value at t equals infinity. This case, it starts at maximum value and it goes to 0 as t goes to infinity, right? So one goes up, one goes down. This is equal to Q max e to the minus t over RC. So when t is 0, we get Q max, and when t goes to infinity, we get 0 for the charge on the capacitor. What's the current? It's the same. I think in the book they throw a minus sign in there. But as far as we're concerned, we don't care about the direction. We know the direction, right? We're going to look at the situation and figure out the direction of the current. But it's basically the same equation. It starts at its maximum value. In both cases, the current starts at its maximum value and decays to 0 as time goes to infinity. So this is the same. I don't really worry about the minus sign. I know the direction's the opposite direction. All right. All right, let's take a look at this one. Circuit's been connected for a long time. Find the potential difference across the capacitor. That's the first thing we need to do. It says it's been connected for a long time, so what does this circuit look like? Looks like this. You do not need Kirchhoffs for this. Nothing, right? Nothing is going through, no current is going through that capacitor. It's been hooked up for a long time. That capacitor is in a steady state. No current is going through that branch. We can remove the whole branch with the capacitor. This is what our circuit looks like as far as current is concerned. If you prefer, we can draw it like this. Same thing. But if it helps you spot what's going on, get your pliers out and bend the wires and make them straight if you'd like. That's fine. As long as you understand that this is the same as that. So what does this look like? Actually, you don't even have to treat them as parallel now. You don't have to go any farther because you know the potential difference across each one. What was it? 10 volts? You know you have 10 volts across the 5. You know you have 10 volts across the 10. So that has to be 2 amps. That has to be 1 amp, which means what do you have coming here? 3. You got the potentials figured out now? Let's call this 0. Then this is 10. So the question is, what is this? That has to be 8 because we have a 2-volt drop. And what is the other side? That has to be 2. Think about like hiking trails. You were standing up here at 1 minute where it was, I'm running out of colors here. You were standing here at 10 volts and you go to the left through the 1 ohm resistor, and you have to drop by the voltage there, right? That's 2 amps times 1 ohm is a 2-volt drop. So if you were at 10 and you go through that resistor, you have to be at 8. But if you took the other path, if you went through the 8 ohm resistor, 8 times 1 amp is 8 volts. You have to drop by 8 volts when you come out the other side. You're going to be at 2. So our potential difference across the capacitor is a difference between 2 and 8, which is 6 volts. Okay, let's do part B. Remove the battery. Over what time interval does the capacitor discharge to 1/10 of its initial value? Remember, if it helps, get your pliers out and bend the wires a little bit. That's the same thing, right? And this is the same thing as that, right? It doesn't matter what order the parallel paths are in. These three things are in parallel with each other. All right, we have an RC circuit. We got most of the way there. We have to finish it though. Over what time interval does the capacitor take to discharge to 1/10 of its initial value? So we're looking for the time when Q is 1/10 of its maximum value. So over here, I'm going to put 1/10 Q max on the left side of my equation. And the right side of my equation, I'm going to leave the same. And I'm going to solve for T. The time when Q is 1/10 of the maximum. I don't even care what the maximum is. It cancels out right there. You may want to review your log properties. We're going to take the natural log of both sides. The ln of 1 over something is the same as negative the ln of that thing. So this is the same as negative ln 10. And the natural log of e to some power is just that power. So this is just negative t over RC. And what R do I put in there? R equivalent. That I found earlier. I should put that everywhere here. Okay, these are typical problems. You don't even need the maximum charge because usually you're asking for what percentage, right? And then it's just a matter of taking the log of both sides, solving for t. Okay. Enjoy your 3-day weekend. I will be online this afternoon. What time? 1 o'clock, right? For our review session. If you'd like to join us, 1 o'clock. There's a different link for it. They're posted on Canvas, but don't use the Canvas link. Just copy it and paste it into your browser. All right, have a good weekend, and we'll see you then.